Welcome to Visual Algebra Lecture 5.8, Simply Transitive Actions. A group action, or the G-set it defines, is transitive if its action graph is connected. That was the topic of the previous lecture. An action is free if the stabilizer of every element is trivial. This means that it is as uncollapsed as possible. Actions, or G-sets, that are transitive and free are called simply transitive. In this lecture, we'll see that every simply transitive action is isomorphic to a group acting on itself by multiplication. In other words, the simply transitive action graphs are precisely the Cayley graphs. Then, we'll see a number of examples of simply transitive actions, mostly from tilings of polygons, polytopes, the xy plane, and even the hyperbolic plane. There will be lots of fun, colorful pictures in this one, even for this lecture series, so you're not going to want to miss it. Let's get started. In the last lecture, I started with a natural question, which was, given a group G, what are its possible connected G-sets, or action graphs? In other words, if we take a group, say, D4, which of the following can arise as an orbit of an action by G? Well, we've seen this one, and we also saw this one as well, but we have not seen the others, and in the last lecture, we understood why we can't. Basically, these three do not arise as the result of collapsing the Cayley graph of D4 by the right cosets of a subgroup. So last lecture was on these connected action graphs, and those are called transitive, or at least the actions in the corresponding G-sets are called transitive. I also defined in the previous lecture what it meant for an action or corresponding G-set to be free and faithful. In particular, it is free if the stabilizer of every set element is trivial. In other words, the action graph is completely as uncollapsed as possible. There are no non-trivial loops from anywhere. So you don't see anything like this, no loops like this, but also nothing like this where you have RF, which is a loop from a non-trivial element in D4. And free actions are going to be one of the focuses of this lecture. It's also worth defining what a faithful action is. That just means that the entire kernel is trivial. And that's a weaker condition than a free action, because remember, the kernel is the intersection of all the stabilizers. So if all of these are free, then the kernel is certainly free as well, but you can definitely have a trivial kernel where some of the stabilizers are not trivial. So in the previous lecture, we classified all transitive actions. And in this lecture, we will classify actions that are transitive and free. But first, let's see a few examples of actions that are free and not transitive. Recall that we've seen some that are transitive and not free. In particular, the two examples up here that actually arise are transitive actions that are not free. Let's now see an example of an action that is free but not transitive. The symmetric group S3, generated by adjacent transpositions, 1, 2, and 2, 3, acts on the permutations or rearrangements of the word 1, 2, 3, 4 via a homomorphism where pressing the 1, 2 button swaps the first and second coordinates, and pressing the 2, 3 button swaps the second and the third coordinates. We've seen this before, and here's an action graph. Just here, I'm not including anything that moves the fourth entry. So the last digit of each of these connected components is going to be the same. Notice that these all end in 1s, these end in 2s, these end in 3s, and these end in 4s. The gray lines here are just added for reference. They're not part of the actual action graph. So this is free because the stabilizer of any set element here, or word, is going to be just trivial, but it's not transitive because there's multiple connected components. So we'll see that actions that are free are as unwound as possible, which means they're Cayley graphs, almost. In this case, it's a disjoint union of Cayley graphs. An action of a group G on a set S is simply transitive if it is transitive and free. So that means it's connected and as unwound as possible. Here are some simply transitive actions that we have seen. This is D4 acting on a set of 8 configurations of the square. This is S3 acting on 6 permutations of the word 1, 2, 3. And this is Z2 cross Z2 cross Z2 acting on the 8 configurations of 3 light switches. What do you notice? These are all Cayley graphs, and there's a reason for that. Every simply transitive G action is isomorphic to G acting on itself by multiplication. Remember, my term isomorphic for action means that the actions are equivalent, and the isomorphism between the corresponding groups is the identity map. In other words, the actual G sets are isomorphic. What this is saying is that simply transitive G sets are just groups. Remember, G sets are like a generalization of groups, but the simply transitive ones are the actual groups themselves. Okay, let's prove this, that every simply transitive G action is isomorphic to G acting on itself by multiplication. And the proof will be completely analogous to what we did in the previous lecture, that every transitive G action is isomorphic to G acting on a set of cosets by multiplication. So actions are isomorphic, recall, if they are equivalent, and the isomorphism between the groups is just the identity. So we have to define a map and prove that it's a bijection and that it commutes with the action. So we're going to do exactly like what we did in the very first lecture, lecture 1.1. We'll take our abstract action graph over here and declare a state to be the home state. Let's call it S. And that's going to correspond to the element E. So over here we have an element E. And then every other element in S we can get via a path from here. So this element we can get via a path corresponding to X, maybe also a path corresponding to Y. You know, there's going to be multiple paths. And so we just label this node with any of the group elements corresponding to any of the paths. But as we saw in the first lecture, those group elements have to be the same. Anytime we have different paths, they correspond to the same group element. We have to actually prove this here. So our map is going to send S to the identity, but it's going to send every one of these elements to, so S dot phi of X gets sent to X. So that's what we got to prove is well defined. So let's say that we have 2 different paths getting us from S to that element. So let's say that S dot phi of X equals S dot phi of Y. Well, that is the same thing as saying S dot phi of X, phi of Y inverse equals S. So I'm just moving this over and then moving the inverse inside. And that is the same thing as saying that S dot phi of X Y inverse equals S. And that's the same thing as saying that X Y inverse is in the stabilizer. I'm writing H, but I don't think we're actually going to use H. But because this action is free, that means by definition that the stabilizer of every element is trivial. So the stabilizer is just a trivial group, and that means that X, Y inverse equals E, or equivalently, X equals Y. And that's what we had to show. We had 2 different ways to label this set element to get there from S, and both of those, when we apply this function, end up to the same place over here. So that's what it means to be well defined. And then injective, or one-to-one, we just go in reverse. Suppose we have two set of elements here that get mapped to the same place. So suppose that x equals y. We have to show that they were the same to begin with. So x being, and as we did last time, we just reverse this. We start here, and x equals y is equivalent to x, y inverse is E, which means x, y inverse is in the stabilizer of S, and we go up here, and we end up back here. So let's just reverse the well-defined argument, and we get injectivity. And then for surjective, or onto, well, this one's pretty easy. We just take an element in the codomain, call it x, and find a preimage. S dot phi of x is one. So take x in G, and then sigma of S dot phi of x equals x, and therefore the map is surjective. And that's all we had to do. Well, at least to prove that this is an actual bijection. Now we have to show that it commutes with the action. But that is straightforward. If we take an element here and we follow the G path, that is press the G button and then apply sigma. So this sends us to S dot phi of xg, apply sigma, we get xg. That's of course the same thing as applying sigma to get x, and then multiplying by g. And here I'm using the same notation for the action in both sides. Some people might quibble with that and say I should use like psi or theta, but I'm fine with using the same thing for both. And that's the end of the proof. The rest of this lecture is going to be a little bit like show and tell. I'm going to go through a bunch of really neat examples where we have simply transitive actions, because every time we have one, we naturally have a group structure on the underlying set. We can build a Cayley graph. And one place where simply transitive actions arise are tilings. Here's a basic example. Consider the abelian group Z cross Z generated by, say, A and B. This acts simply transitively on the set of unit squares in the xy plane. And here's an example. Here are the squares, and I say the unit squares, I mean assuming that we already have a coordinate system. So we can take any square and declare it to be the home state. And then if we press the A button, let's say that we move one to the right, and if we press the B button, we move one up. Here is a Cayley graph. So this home state is sometimes called a fundamental chamber, and it allows us to label every other chamber with a group element, which corresponds to a path for how we get there. So AB squared means we go AB squared. And of course, we could have labeled it with something else like B squared A or A squared B squared A inverse. Typically, we like to label it with a minimal path, but we don't have to. The previous example was of an infinite group, but there are plenty of finite groups that act simply transitively and define tilings as well. One example is the dihedral group D3, generated by two reflections A and B. This acts simply transitively on the 6 regions of a hexagon. So here are several pictures of this, and I should say that there's 2 ways to define how we label the regions. So here's a hexagon. Let's say that A is green and B is blue. Then one thing we can do is take one of these regions and put a line or hyperplane along one wall and corresponding to A, and another one corresponding to B on the other wall. So now when we press the A button, we reflect across the corresponding line. So if we start here and then we do, so this is A and that is B. And if we want to do AB, remember we're reading from left to right, we do A and then we reflect across the blue one and we get AB down here. However, there's another perfectly valid way to do this, is we could take our fundamental chamber and we could call one wall A and one wall B, and then we could just repeat that process like this. And now if we reflect across A, we get over here, and then we reflect across B, we get over here. And notice that's different than it is down here. Without going into details, may not come as a surprise to you that one of these arises, or one of these is a left action and the other one is a right action. I think generally the right action is a little more natural because we are writing things from left to right. Now, I will say, if you see examples of this out in the wild, like on Google and elsewhere, you might see these things switched, calling this a right action and this a left action, and that will happen if you're reading things from left to right, which is, again, probably more common. So these define Cayley graphs. I think it's more natural to construct a Cayley graph with the right action, because we can just, that's what we did in the previous slide. We just put a node in every region, and then we put an edge anytime that we have two regions that differ by crossing a wall. So this is D3, but we can also do the same thing for D4. It's going to act simply transitively on the 8 regions of a square. At this point, the astute viewer might realize, wait, n equals 3, and we have a hexagon with 6 sides. N equals 4, we have a square with 4 sides. Why not an octagon? Well, we definitely could have done this with an octagon. And let me see if I can draw this. It's not necessarily the easiest. These have to be parallel lines. So this might not be perfect. But why did I choose to do a square instead of an octagon? Well, the square is going to tile the plane, and a hexagon is going to tile the plane as well. So as we'll see shortly, if we have this group and then we add one more generator, let's say this line over here, maybe it's easier over here, then we will get an infinite group that's going to define a tiling of the entire plane. Over here, I need to add this hyperplane, or this picture, just this line. So this is with n equals 3 and n equals 4, and we can define something like this for, general n, d5 and pentagons and d6 and or d7 and septagons, etc. They will not extend to the plane the way these things do. But you can definitely draw a picture like this for any n. You can really draw a picture like either one of these, n versus 2n and n versus n, for any dihedral group. Here's a more complete picture for what I just tried to explain. In both previous examples, adding a third reflection generates a tiling of the plane. And we call the resulting group an affine group. This is not the standard notation, but I will use it because I don't want to introduce the whole notation that is typically used in this field, just for these examples. And these groups act simply transitively on the chambers. This is the picture of the left action. But of course, there's a corresponding one for the right action, and I will start with the triangle picture first. These groups that define tilings of the plane are called affine Weyl groups, whereas groups that define tilings of polygons or polytopes are the finite Weyl groups. The group that I just showed you, the affine version of D3, is better known as the affine Weyl group of type A2. And A refers to the fact that the fundamental chamber is a triangle, and 2 is just the dimension. So we can do this in any number of dimensions. This group acts simply transitively on the chambers of the following tiling of the plane. So if we declare some state and we call it the home state, we can label all the chambers like this. And some of the labels are pretty clear. This has to be A, this has to be C, this is AC, and so forth. But down here, there's a lot of things that we could label this with, and I don't know a canonical way. There's generally going to be multiple shortest paths from the home chamber to somewhere else, and I don't know the best labeling, but it doesn't really matter. This puts a group structure on the set of triangles, and here is a Cayley graph. And the presentation of this, well, it's generated by A, B, and C, and I've color-coded these so you can look at the corresponding wall. And these are all reflections, so A squared and B squared and C squared are the identity, but also now for every pair of reflections, I have to tell you if you multiply or you compose them, you get a rotation. So what is the order of that rotation? So if you do A and then B, that is, you start here and you do green and blue, that is, you can just see it, that is a, or in either order, or in one order it's going to be this way and the other order is going to be that way. That's a 120 rotation. So that has to have order 3. If you do A and then C, that's doing green and red. So if you do that, let me do it from somewhere else. So if you start here and you do green, red, that's also going to be a 120 rotation. So that AC has order 3. And finally, BC is blue, red. If we start anywhere and we do blue, red, that's going to be a 120 rotation. So that will have order 3 as well. And it's not entirely obvious that there are not any other relations than this, but I think it seems reasonable that you have these, because you have this geometric interpretation, that you should only have these relations. The affine version of D4 is better known as the affine Weyl group of type C2. C comes from the fact that you have this type of triangle as a fundamental chamber, and this group acts simply transitively on the chambers of this tiling of R2. So here are the chambers, and here is a Cayley graph and a presentation. We can once again use A, B, and C as generators. These are reflections, but now when we do A and B, notice that the green and the blue things are 45 degrees apart. So when we start here and we do A and B, this is a 90 degree rotation. So that's going to have order 4. Similarly, if we do A and C, we do green and then red. Let's go down here. So we start somewhere and we do green and red. That's also going to be a 90 degree rotation. So that has order 4. And then finally, B and C, the blue and the red, go here. This is actually, these are orthogonal or perpendicular. So you do blue, red, and this is a 180 degree rotation. So that's going to have order 2. And now I want you to notice that if you draw one of these triangles that defines the fundamental chamber, and you look at the angles, well, this is pi over 2, and then the other two angles are pi over 4. And that is not a coincidence. Notice 4, 2 appearing right here, 4, 4, 2. In contrast, in the previous slide, we had a fundamental chamber that was defined by an equilateral triangle. So this was blue, green, and red. And all of those angles were pi over 3. So when we had the presentation, instead of 4, 4, 2, we had 3, 3, 3. So there's this neat connection between the geometry and the algebra. And Weyl groups are actually a special case of something that are called Coxeter groups. And these are groups that are generated by reflections. And by definition, they are generated by elements of order 2. And then for every pair of reflections, you have to specify the order of the product. You can think of that as a rotation. And this is a really neat area that involves combinatorics and algebra and geometry. Whenever you have one of these groups, you can build a vector space that this group acts on. And you get a tiling like this. Now, that space might not be in the plane. You know, it might define a polytope, or it might live in the hyperbolic plane. And we'll see some of those later in this lecture. The presentations of the affine Weyl groups that we've seen, we just saw a geometric interpretation of them. They are encoded by labeled graphs that are called Dynkin diagrams. The nodes are the generators of the group, and then we label an edge with the exponent that we saw in the relation. So if there's an edge from Si to Sj, then and SISJ to the Mij is 1, then we label that with Mij. So here's an example of how we can encode. Well, here's the first two ones that we've seen, the affine version of D3 and the affine version of D4. So I should also say, I didn't write this here, but anytime that we don't have an edge, we can assume, so let me write this down, no edge means Mij equals 2. So here we have a triangle, because every pair, we have AB cubed equals AC cubed equals BC cubed is the identity. And then over here, we have AB to the fourth equals AC to the fourth equals BC squared. And because of that, we don't put an edge here. So notice that if we have SISJ squared equals the identity, that's the same thing as saying everything SISJ equals SJSI, because these things have order 2. So the exponent is 2 if and only if the generators commute. And as we saw in the previous example, when we had a commuting pair of generators, that meant that the axes of reflections are orthogonal. And we know that two reflections will commute if and only if they meet at the axes are orthogonal. So that's why we don't put an edge here. You can really think of this graph as anytime we have non-commuting generators, we put an edge and then a label for what the corresponding reflection defined by the product is. And whenever we don't have an edge, that just means that B and C don't commute. So we've seen these two. Here's one that we have not seen. There's an affine version of D6, and that is sometimes called the Weyl group of type, affine Weyl group of type G2. And this is one, so these two exist in any number of dimensions. This one does not exist in any number of dimensions. It's just special in 2 dimensions. And here's how you can define it. So D6 acts simply transitively on these 12 regions of a hexagon. Here's the left action, here's the right action, here's the Cayley graph that it defines. And then we can tile the plane with this. In other words, we can add one more, maybe I should draw it here, one more plane and get an infinite group. And here that is. So here's a fundamental chamber, and here's the Cayley graph it defines, and here's the presentation. And let me just remind you several things. So let's first draw this fundamental chamber. And I want to show you that this angle here is pi over 2. This angle up here is pi over 3. And this angle here is pi over 6. And you can tell that because there's 12 regions that at one of these green-blue points. There's 6 regions that go around a green-red point, and then there's 4 regions that go around a red and blue point. Those are harder right there, harder to find. So you can read these exponents off of the geometry, and then finally the Dynkin diagram. It was on the previous slide, but I think it wouldn't hurt to put it here again. C, B, and A, and then sometimes these are called bond strengths, 3 and 6, and then C and B commute algebraically because of this, and geometrically because they meet at the 2 axes are orthogonal. I mentioned what a Coxeter group was earlier. Here's a formal definition. It's a group generated by so-called reflections, that is elements of order 2, with the following presentation. So for every pair of reflections, we have to specify the order. And it's a fairly non-trivial fact that the order of this product is always going to actually be Mij and not a proper divisor. So if SI/Sj equals 12, you might think, well, maybe it actually has order 3 or 4 or 6 or 2, but no, it will be 12. So when you have a group like this, you can always build an n-dimensional vector space on which this thing acts simply transitively or defines a tiling. And like Weyl groups, this can be encoded by a Coxeter graph. So your nodes correspond to generators, Si and Sj, and we typically, anytime that these do not commute, that means Mij is bigger than 2, we label that edge with this exponent, sometimes called a bond strength. Now, a lot of Coxeter groups that come up in practice have a lot of 3s in these presentations. So it's convention to any time that you have a label of 3, just don't label it. So when you see unlabeled edges, you can assume they are 3. And so there are 3 infinite family of Weyl groups that define tilings that we've seen. So there's the one of type AN, which actually let me do this a little bit differently. So here's Sn minus 1 and S1, S2, S3. So then there's the Weyl group of type B. I'm going to hold off on the tildes for just a moment. So Bn. So we have Sn, Sn minus 1, S1, S2, S3. I didn't need to write all these generators. And then there's one of type Cn, and Sn, Sn minus 1, S1, S2, S3, and so forth. So we also need a bond strength here of 4 and a bond strength of here. So all 3 of these things define actually finite Weyl groups or finite Coxeter groups. This corresponds to the symmetries of a tetrahedron or a simplex. This corresponds, and these things are actually the same. They correspond to symmetries of an n cube. Then all of these have affine versions, which is where you add that extra reflection in, and you go from tilings of a finite polytope to tilings of n-dimensional space. So for this one, if you add a vertex here, so this is going to add a generator, change the presentation, the an turns into tilde an. The finite one becomes infinite. For the affine Weyl group of type B, we add S naught here, and we get this group. And then for the affine Weyl group of type C, we add this S naught here, and get this. So affine Weyl groups of type B and type C define different tilings, but they come from the same finite tiling. So this is a bit of a preview. I encourage you to Google this if you want to learn more about Coxeter groups. It is a really fun topic involving combinatorics, algebra, and geometry, and even some topology as well. Now, as I mentioned, every Coxeter group defines a tiling, but many, if not most of these, are not going to be of a polygon, polytope, or of the plane. In general, they will define tilings on some hyperbolic space, and that's where the geometry part of this comes up. So understanding the connection between the algebra and the groups and the underlying space. The last tiling of the plane that we saw was the affine Weyl group of type G2, and that arose from a tiling of a hexagon with 12 fundamental regions, and we extended that to the entire plane. And here's the Dynkin diagram. If we change this 6 to a 7, then we get a different tiling that does not tile the plane. It looks like this. We have 14 triangles around a point instead of 12. So if we draw this fundamental region, let me use the same colors that I did before. so that's blue, red, and green, well then this angle is pi over 2. That's B and C doesn't have an edge, so that's strength 2. This is pi over 3 because of that 3, and this one is now pi over 7. So for these triangles do tile a space, but it's not a Euclidean space. It's a hyperbolic space and looks like this. So this picture, the triangles in this picture, have an algebraic structure of this infinite group. We can build a Cayley graph with this. Oh, and I should say, if you haven't seen hyperbolic space before, all of these triangles are the same size. So this is like the line at infinity. And so even though they look smaller, that's just a realization of how it's drawn on the map. So, you know, when you see a map of the world, Greenland is drawn bigger. That's kind of the opposite. When you have, that's a positively curved space, so it distorts things toward the boundary to make them look bigger. When you have a negatively curved space, it distorts things toward the boundary and makes them smaller. But all these triangles are the same size. Isn't that neat? I want to finish this lecture with a really fun example of a tiling defined by a group that's called the projective special linear group over Z. So this is the group, well, it's the special linear group. It's a set of all 2 by 2 matrices with integer coefficients with determinant 1, but we're going to quotient out by the identity, the negative identity, which means that every matrix is equivalent to its negative. This comes up in number theory. This is called the modular group. That's why I do not like the term modular group for what I call the special abelian group. And it also comes up in hyperbolic geometry. This is the hyperbolic plane. This is the group of hyperbolic isometries. Actually, I should say that it's related to hyperbolic isometries. Let me just leave it like that. So what you're looking at here is a model. It's called the upper half plane model of hyperbolic space. There's another model called the disk model that you saw in the previous slide. So in the previous slide, the outer boundary circle was the point at infinity, and here the x-axis, or the real axis, is the point at infinity. These lines here are straight lines in the hyperbolic space. So this looks like a straight line, but these are also straight lines, meaning that these are geodesics, so that the shortest path between this point and this point lies along the circle. So it's really because if you want to measure distance in Euclidean space, you normally have a curve and you measure it, you integrate like this, but in hyperbolic space, you have to do f of t divided by y dt. So that means that you can never actually travel from here to the real axis. This is like an asymptote. So these are straight lines. All of these things are triangles. Well, they're called ideal triangles, and that's because, let me try to draw this. I don't know how well I'll be able to do it. An ideal triangle has at least one angle that is 0 degrees. So these two angles are pi over 3. You can see that because if you take any one of these triangles, so this point right here is going to, there are 6 regions around it. So this is each one of these is pi over 3, and same with this one, this point down here. There's also 6 regions around it. But if you look at the other point here, there's infinitely many things around it. So this is really a 0 degree angle. So that's why it's called an ideal triangle and not a triangle. So this is a tiling of these ideal triangles, and they're all the same size, meaning we can map one to the other. They all have the same area. And you may be wondering, what about this thing right here? Well, yes, this actually is, this thing here actually is an ideal triangle because these two lines are parallel and they meet at the point at infinity because of this metric. There is a hyperbolic reflection that sends this region to this region that's right below it, right here, and it sends this to any other ideal triangle as well. So this is a really neat topic involving, so you might see this if you study hyperbolic geometry. You also might see this group if you study number theory. It's called a modular group because it's related to modular forms. These are examples of what are called Mobius transformations. In general, if you have a matrix like this, say A, B, C, D, this defines the transformation that sends Z, a complex number, to A, Z plus B over C, Z plus D. And that's where the hyperbolic isometries come from. And notice that if you multiply this matrix by -1, then you get the same function, which is why we mod out by this size 2 subgroup. So these are called Mobius transformations. And this is just a really neat example. And what it's saying is that this tiling of hyperbolic or of ideal triangles has an algebraic structure. We can build a Cayley graph. Well, you know what? Here is the Cayley graph. I've showed it to you. Okay, so that's about really all I want to say. A theme of this lecture, simply transitive actions, was finding Cayley graphs in unusual locations. For example, like tilings. And there's others that are not coming from tilings. You know, we saw the 3 light switch group. We saw the configurations of the square. We saw the Rubik's Cube group. All of those are examples. The Rubik's Cube group acts simply transitively on the set of states. And there are other examples as well. So if you sometimes a combinatorial set with an algebraic structure is called a torsor if it admits a simply transitive action. And some of these are from tilings or Rubik's Cube states or things like that, but there's others that are unexpected. And one that I want to mention is involving the spanning trees. I'm not going to show you examples. I don't really have visuals made. But if you take the spanning trees of a graph, let me call it gamma instead of G. G is for group. Every graph is going to have a collection of spanning trees, which is just, a combinatorial set. But there's something called the critical group of a graph. It can be defined via the Jacobian matrix. It can be defined via something called chip firing games, or it can be defined via an operation called rotor routing. It's this really neat group that acts simply transitively on the spanning trees of a graph for any graph. And that means that the spanning trees have an algebraic structure, which is in no way obvious. And this is an abelian group. So I encourage you to Google this, go down that rabbit hole, and check it out. Now, I put the word torsor here. So some people say that the spanning trees are a torsor for this critical group. And in fact, I have a recent paper involving the word torsor as well, where I look at a combinatorial set, that is a set of independent sets of a graph, and there's a group that acts on this via something called toggles, and you can represent the dynamics in terms of these zeros and ones, these cellular automata, and we notice that there's this weird group action on the set of zeros. We call them live entries, which means that this action involving independent sets has a group structure, and it's an abelian group. So if you Google my name and torsor, I'm sure you'll find that paper. And there's many other examples of torsors as well that I encourage you to check out. And if you know some of them, please leave a comment in this video. So this lecture, we talked about simply transitive actions. Before, we talked about transitive actions, and a general theme for the last couple lectures has been G-set isomorphisms. When are two G-sets not only equivalent, but isomorphic? In the next lecture, we'll talk about G-set automorphisms, and more generally, G-set homomorphisms. And that's going to be the last of this kind of 4 lectures, like a mini series within chapter 5 about the structure of G-sets and maps between them. And then we'll move into CELO theory, and that'll be the end of chapter 5. So make sure you stick around for at least the next lecture. It's kind of be a nice way to close out this theme. And it's hard to judge this because there are so many really neat pictures in this chapter and ideas, but I think maybe my favorite one is in the next lecture. And I think it will be a surprise and sort of an aha moment for even the seasoned expert out there. So don't go anywhere. I'll see you then.